these things didn't work.
Okay, good morning, everyone. How the shell goes. Okay, put your question on chat. Okay, 17, 43, and 46. Let me look at them. Okay. I will do 17, and you're gonna be spending the whole hour working on those problems. So do not worry about them. But I will do 17 first, and then we're gonna start. And by the end of the hour, you guys will understand everything. So the main thing I want you to know from yesterday, so let me write it down, is the volume of a shell. Okay, so this is my shell. Looks like this. And it's a shell, so it's a cylindrical shell, so there is a certain thickness right here. A little bit of a thickness. Very, very small. That's my delta Y and delta X. And from here to here, that's called the height of the shell. That's the height. That's the center. And the radius, and as I said, we're approximating it because the thickness is very small, very, very thin. It's the delta X. It's like very small. Or you can think of it as from the center, of course, all the way, either the outer, if you want the outer radius or the inner radius, I don't really care. It doesn't really matter because they are very, very close to each other. So that's really my R. And the volume of a shell, that's the only thing we want. Volume of a shell is 2 pi times the radius, which give me the circumference of the circle. We times it with the height. We times with the height, which is gave me basically the area of the rectangular prism, and you multiply the whole thing by the thickness of the shell, which basically gave me the little volume. So that's really what we want to do. The only thing I want you to learn, and I did put approximately because I'm not making much difference between the little bit here, this radius up to the inner radius if you want, and the outer radius, because they are very close to each other. That's why I have approximately equal. All right, so we start with number 17, and then we start doing a lot of problems. So 43 and 46 will not be hard anymore. But I will start with 17 because it's basic. So let me draw. Okay, so we have y equal cosine x squared and y equal to 0. That's the region. X between 0 and the square root of pi over 2. And the rotation is about the y-axis. That's the axis of rotation. All right, as usual, we have to graph. And since this was assigned home, so I expect you to use decimals to graph all those. So this is my axis of rotation. Important. Y equal x between 0 and the square root of pi over 2. So that's the square root of pi over 2. So if I plug in square root of pi over 2 in here, I will have cosine pi over 2, which is 1. So I imagine the graph, and if x is 0, that's 0. So I imagine the graph will go like this. And then it's going to go differently, but we only care between 0 and the square root of pi over 2. So this is the region in question. And we're rotating about the line, the y-axis, so we're going to get something like that. Okay. And we want to use the shell method. The shell method, it means we're taking the slices parallel to the axis of rotation. So that's really my typical slice. So I'm fixing my xi. You can put it at the right or the left. It doesn't actually matter at all. And this is my little delta x. So now forget about everything. Just focus on this line here. Focus only on this one, on this little piece, and rotate it. So xi changes, of course, because the idea is we're splitting this into pieces. So this xi from here to here is changing. So I'm going to rotate this a little bit. Shells are easy to rotate. The geometry is fairly simple. I'm going to get this shell. I want to find the volume of a shell. So I focus on typical shell or cylindrical shell, whichever you use. To find typical shell, when I say I focus on it, it means I want all those pieces written down. My radius and the height and the thickness. And finally, the volume. So every aspect of it. Okay. So the radius, as we said yesterday, that's the center of rotation, and that's the base of the shell. The radius is from the center of rotation all the way to here. That's my radius. My radius changes with the shell. As I take a piece here, the radius here is larger than the radius for that. So the radius is not fixed. The radius is changing with definitely where my shell is. So my radius in this problem is the xi. The height is from here to here. Now this is the function cosine x. So this is going to be cosine xi squared. That's the height. The thickness is the little delta x. And here x is my variable because in my mind, I'm dividing this into pieces and I'm rotating every piece. So I am filling the whole region. As I said yesterday, you can think that I'm filling it with onion rings. Or another way you can think about it's like a Russian doll. So I'm inside, I have like, if you remember, you have those Russian dolls where you have a doll inside another. That's how I'm filling the volume. The volume is 2 pi times the radius times the height times the little thickness, which make it into a volume. So now the volume of the whole thing is the integral from. Now they gave me everything. So the integral is very clear. It's from 0 to the square root of pi over 2 of 2 pi x cosine x squared dx. And now it's the integral that we have to evaluate. 2 pi is a constant. I take it out. Integral from 0 to the square root of pi over 2 of x cosine x squared dx. Now, how do we evaluate this integral quickly? Stare at it. It shouldn't take you too long. What do you see?
U substitution.
Absolutely, U substitution. Because we
Substitution.
Yes, exactly. Because we see an inside function, x squared, and we see its derivative almost staring at us up to a constant. So we definitely have to do a U substitution. So let's do that. Okay. So we're going to set U equal x squared. The du is the 2x dx. Now I'm going to change my limit. If x is 0, my u is 0. If x is the square root of pi over 2, my u is simply pi over 2. And now I'll take this integral and everything in terms of u. I will get 2 pi times the integral from 0 to pi over 2 of x dx is a half du. So this x combined with this dx gave me the half du. The cosine x squared is the cosine of u. So finally, I will get a half is a constant. I take it out, gives me a pi. Antiderivative of cosine is the sine, evaluated between 0 and pi over 2. So finally, I will get pi times value at the upper. And now, since I changed my limit of integration, I don't really need to go back to x anymore. I am done. So this will be equal to pi times sine of pi over 2 is 1. Sine of 0 is 0. So I will get equal to pi. Okay. Any
I
question?
have a question. I have
Yeah.
a question, Professor Elias.
Go ahead.
So I remember I was encountering one of these problems. If you change the parameters, let's say you split up it into two integrals, could you use can you change the parameters and then add them back together if for like one of the problems? Do you understand what I'm saying?
I'm trying to repeat.
So like let's say for an example, I split up the integral into two things. For one of the integrals, I used substitution and changed the parameters, but for the other one, I didn't. Could I then change them or would they be like different?
If you're doing it this way, isolate each one. Do it by itself and then combine. So you can
Okay.
avoid any mistake. So
Okay.
I don't know if you understand what I said. Let me see what I want. Suppose you're doing the following integral. Okay, I'm trying to answer the question you, okay. Let us say I have here e to the x plus x cosine x squared. Is this what you're referring to?
Yes, exactly.
Yes. So if I am doing it, I definitely split this way. All right? And then I will take this integral, take it to the side, isolate it, evaluate it fully because it needs a substitution. So this one I totally isolate. This one I do it the way I want. I don't have to isolate it. So this would be e to the power square root of pi over 2 minus e to the 0. I don't need to isolate it. This you isolate, evaluate, and then plug the value in here.
Okay, that makes a lot more sense. Thank you. Appreciate
Okay,
it.
totally. You have to separate them. You have to separate them. Otherwise, you will be confused with the u. This one does not require a u. That's e to the x. You do it by itself. This one requires a u. You take it to the side, evaluate, do everything you want. The answer has to be here without anything.
All right, thank you very much.
Sure. All right. So now, as I said, today I will not introduce anything, basically nothing new. We're going to work a lot of problems together. So the first problem is, none of them is hard, but you guys have to be with me so you can answer everything. And what is my pen? Okay. So I'm going to take the following region. Okay. Easy region. So the region should not be a hinder for us. So let's see, R is the region bounded by whatever, y equal x squared, and let us say y equal root x. Okay. And the question is, find the volume using the shell method. Everything is the shell method for now. So using shell method, find the volume obtained by rotating the region R about the line x equal to 2. Oh, sorry, x equal minus 1. All right, and my question is the shell method, even if use shell method. So that's the first one. So I'm going to draw the line, everything, and you guys will have to help me out. So this is my region, y equal x squared, and the square root of x. So this is the intersection point. We found it a million times. And this is my y-axis. And x equal -1. This is -1 in here. And this is my axis of rotation. So I'm switching the axis of, instead of taking the y-axis, I'm taking an axis parallel to the y-axis. The way we will approach it, so now, of course, everything is bigger. So if I take it about the y-axis, now I'm enlarging everything. So something like that, we draw it. The principle is the same. The principle is the same. So I'm going to take, since I'm using the shell method, I'm taking those slices which are parallel to the axis of rotation. And so this is my one in here. And I'm going to take my xi. As I said, you can take it to the right, to the left. It doesn't really matter where you take it. So this is my xi. And this is my delta x. And even if you write x instead of xi, it's all right with me as well. And we're going to rotate. So when I rotate this, remember that's my center of rotation right now. So I'm going to rotate like this. So it's going to go all the way here. All the way here. That's my axis of rotation. Okay. And now this is my shell. And we have to figure out everything about the shell. So typical shell. Okay, to find everything, I need the radius, the height, thickness, and finally the volume. Once I have that, I have everything I want. Okay, and now let me go back to you. I want you to look at this very carefully. This is my axis of rotation. And this is my typical shell. You know, the shell is changing. The shell is changing with xi. If I have an xi here, I have one radius. Every time I take a different slice, I have a different radius. All right, now back to you. What is the radius?
I don't know how often.
Are you asking a question? Okay, what's the radius of the shell? Every one of you.
Would it be x plus 1?
It will be x plus 1. Do you agree with them, with your classmate? Absolutely correct. The radius is going to be from here all the way to here. So the only thing is that the radius is going to change. So the radius is from here all the way to here. You can either stare at it and you tell me it's xi, you're adding 1, correct? Or you can say, I don't care, xi, the right side minus the left, which is xi plus 1. So the only thing changing is actually the radius. The height is not changing here. I meant even if I rotate about the y-axis, the height is the same. It's the upper value, which is the square root of xi, minus the lower value, which is xi squared. So my height is the same. My thickness is the little bit of delta x. And my volume is easy now. It's 2 pi times the radius times the height times the little delta x. So that's the volume of a typical shell. So now the volume of the whole thing is the integral from 0 to 1 of 2 pi x plus 1 square root of x minus x squared dx. Okay. Now, how would we evaluate this integral? I will not evaluate it because I would like to do more problems. How would you guys evaluate this integral? How would you evaluate?
Combine or like
Keep going.
cross multiply, distribute. Yeah, what
Distribute, exactly. To evaluate, distribute. Correctly. We just have to distribute and proceed. Once we distribute, it's a fairly easy problem. All right. Okay. I will do the same problem along the same line, but I'm going to change the axis of rotation. Okay, so B. So it's the same region. I'm not changing the region. And and the axis of rotation is the line, I don't know, x equal to 2, for example. So as you realize, the problem becomes fairly simple once we understand the concepts here. So, okay, line x equal to 2. Okay, I draw, and then we set up the integral. So again, this is the root x, and this is the bottom one is the x squared. And this is 1, 1. And right here it's 1, and I'm rotating about the line x equal to 2. This is my 2 here, and this is my axis of rotation. Okay. And the principle is the same. I'm using the shell method in all those problems, for now at least. So I'm going to take a slice parallel to the axis of rotation. And down here, this is my xi. And that's the piece that I'm going to rotate. We always focus on the axis of rotation. So this is my axis of rotation right here. So I'm going to draw all the way here. That's really my little shell. Shells are easier than washers, I think. This is my shell. So you guys have now to tell me everything, typical shell. What's the radius? All of you, at least in your mind, tell me, and one of you speak up. Okay. It's, oops, ouch, no, no, the radius. The radius, first let's look at the picture. Is from where to where? From here to here. Do you guys agree with me on the picture? Am I making sense? It's from here to here, from your slice to the axis of rotation. All right, how much do we have from here to here? Look at the picture. Okay, the answer I have on chat is x minus 2. And I said no. Why do you think I said no for this answer? If you compute xi minus 2, are you going to get a positive or a negative number? Absolutely. This is going to give me a negative number. You know, just think on the number line. Remember when I start this whole thing, I started with a number line. And I tell you, if you have 2 points on the number line, what's the horizontal distance between them? It always the right value, whatever it is, minus the left value. That's what it is. So always the right value minus the left value. So why I am talking about that? What's going to be the distance from here to here? Xi, remember, Xi in your mind is not something abstract. Xi is the distance from that point to that point. That's your Xi. So what's going to be the radius? The right value, 2, you take away Xi. It's 2 minus xi. This is going to be a negative number. So the radius is the right value, which is a 2, you take away the xi. This is going to be negative. You're going to have a negative volume, which is not going to make sense. The height is, of course, the difference between them. This is the delta x, and the volume is the volume. 2 pi times the radius times the height times the delta x. So always remember, the horizontal distance between 2 points is the right value minus the left value. The horizontal. The vertical distance is the upper minus the lower. Keep those in mind in those problems. So finally, the volume is integral from 0 to 1 of 2 pi times 2 minus x square root of x minus x squared dx. So this is really the radius, which is really changing. Okay. Now I can give you tons of problem along the same line, but definitely that's not what I'm going to be doing right now. This is, you do it in your homework. Any questions? Okay. Part 2, along the same line, but instead of rotating about the y-axis or lines parallel to the y-axis, I'm going to do the same thing, but I'm going to rotate about the x-axis using the shell method. So this is the problem is here. So rotation about the y-axis, sorry, rotation about the x-axis or lines parallel to them, rotation about the x-axis using the shell method. So I'm going to take the following creation. It's actually in your book because I liked it. So let R be the following creation. R is the region in quadrant 1 bounded by y equal the square root of x minus 2, y equal to 2. Okay, and the question is, find the volume of the solid obtained by the rotating of the solid obtained by rotating R about. Okay, so we're going to use the same region and we're going to rotate it about different axes. So the first one is about the x-axis. Okay. Remember the shell method, I'm using the shell method in all those problems. The slice is parallel to the axis of rotation. The slice is parallel to the axis of rotation. So step number 1, I'm going to graph, of course. Okay. Y equal the square root of x minus 2. I expect you to be able to do that. This is the square root of x shifted to the right by 2 units. Square root of x shifted to the right by 2 units. So this is 2 here. The square root of x is like that. We shift it to the right. So that's the graph of the function. So this is y equal the square root of x minus 2. Y equal to 2, that's it, 2 in here. This is y equal to 2. And I am in the first quadrant, so life is easy right there. So this is the region. And I am rotating it about the x-axis. That's the x-axis. And I'm using the shell method. It means I'm taking slices parallel to the axis of rotation. Parallel to the axis of rotation. So I'm taking, so I'm gonna put here, that's my slice. Okay, that's a typical slice, and I am rotating it about the axis. So this is my axis of rotation. So I'm gonna go right here. Question number 1 before anything else. What do you think is going to be my variable in this problem? X or Y? What is the variable? Absolutely, Y is the variable. I am splitting to cover the region. I am splitting this interval into pieces. So I'm splitting the interval on the y-axis into pieces and covering it. Y is my variable. So this is my delta y from here to here. But my picture is incomplete till I give you a number here, which is my yi. Remember, the yi is from here to here. That's my yi. This is my shell. This is my yi. And now I want to find everything about the shell. I need the radius. I need the height. I need the thickness. And finally, the volume, which is easy once we figure out all the little ideas. And now it's U. What's going to be the radius of the shell? Exactly. Anybody else? Right. The radius is going to be from here to here. From here to here. That's my axis of rotation from here to here. In this situation, you assume that you know the y. You know the y. That's what you know. You know how much you have from here to here. This is my radius. Perfect. My yi. What is my height in this problem? So that's the radius. What is the height of the shell? Of course, the height is from here to here. So this is the height. So it's this horizontal distance from the y-axis here all the way to here. That's the height of the shell. So what is the height of my shell? Yeah, what do you have to do? To find the height, I need the x, the horizontal distance. It means I need the x that correspond to this y. So need right here, we're gonna solve for x. We have to solve. I need a horizontal distance. So let us solve for x. I square this, I get y squared equal x minus 2. It means x is y squared plus 2, right? Oh, why everybody's getting something different? Am I goofing? If I square both sides, I get y squared is x minus 2. I solve x equal y squared plus 2. Am I doing something wrong? Are you guys?
No, everyone else is goofing.
Okay, so be careful. All right. So the height is going to be plus 2. Is that clear for everyone? That's going to be my height. So my height is going to be the yi squared plus 2. Remember, the height, to find the height, it means you're finding a horizontal distance. You have to express it in terms of y. Y is the variable. So the height, there shouldn't be any axis in it. Everything in terms of y. This is my little delta y. That's the thickness of this little shell in here. So the volume is 2 pi times radius, height, finally thickness. So the volume will be 2 pi times yi times yi squared plus 2 times the delta y. Now the total volume equal to. Now I go back and I need my integral. I go back and see, do I have enough info for the limit? Okay, to cover this whole region with those slices, I have to divide the interval from 0 to 2. So I always go back and I switch interval. I need to split into pieces to cover my region. So this is going to be integral from 0 to 2 of 2 pi y times y squared plus 2 dy. And that's a very, very simple integral, the 2 pi, and then you guys know how to go from there. Just distribute and proceed. Equal, etc. Okay. Questions about that? Okay, now I'm going to keep the same region. Basically, I'm just going to change the axis of rotation, but I'm staying with axis parallel to the x-axis. So, okay, so B is, I'm going to rotate about, so it's the same region, but the axis of rotation is changed. So let me rotate about the line, let me see, y equal to 2. That's my axis of rotation. Okay, so graph, proceed. So the region hasn't changed. It means this is y equal the square root of x minus 2. This means this is the line y equal to 2. That's the region. This is 1 here. No, sorry, this is a 2 in here. And the axis of rotation is the line y equal to 2. This is the axis of rotation. I'm using the shell method. It means I am covering it with slices parallel to the axis of rotation. Okay. And usually in your mind, just rotate it. So ask yourself, when I'm rotating, am I getting a washer or a shell? So you should be able to decide once you rotate it in your mind. So I'm going to rotate this around the line y equal to 2. So that's the axis of rotation. So that's the center of rotation. So I'm rotating. I'm rotating. As I said, shells are easy to sketch. The other one are harder. All right. So this is the shell I'm going to get. All right. Now I'm not done with the picture. Something is missing. I have to assign a value here. This is my yi. So it's from here to here. That's in my head what the yi is. And this is the little thickness attached. And then right here, we have to figure out everything. So a typical shell. Again, radius, height, and the rest. Thickness, volume. All right, now back to you. What is the radius of the shell? 2 minus y, do you guys agree with your classmate? I do. Yes. So the radius is from here to here. That's the radius. That's a horizontal, sorry, that's a vertical distance between 2 points. So it's the upper value, which is a 2, minus the lower value, which is the 1. So this is now easy. 2 minus. Very good. Now, the height is like before. So this is the radius right here. That's R. That's the labeling. The height is like before. I know the Y. This is the height from here to here. I need the X. So the height, that's the height. It has to be in terms of Y. And we figured it out a minute ago. It's the Y square plus 2. So the height hasn't changed. The thickness is the delta Y. And the volume is 2 pi, radius, height, thickness. 2 minus the yi square plus 2. So finally, the volume is the integral. Now the integral will go from where to where? What are the limit of integration? Absolutely nothing changed. It's from 0 to 2 because that's the interval I need to cut into pieces to cover this with those slices and rotate every one of them. So that's going to be from 0 to 2. So distribute and integrate. So distribute, then evaluate. Evaluate. Okay. So now we found 2 ways of evaluating volume. Let me a little bit summarize both approach and then give you a problem and tell you, which one would you rather do it by. So you will have a choices now. Some problems are way easier with shell and some are easier with washers. So let us a little bit of a summary. So disk / washer and shell. Okay. In disk / washer, always the slices are perpendicular to axis of rotation. That's how we generate the washer. And in the shell, the slices are always parallel to axes of rotation. So in the shell method, so let us draw the two pictures, some pictures. So for example, I have any region, I don't really care about what region we have. So if we are rotating about the x-axis, these are my slices. Okay, and you just imagine in your head, if I rotate this, I'm gonna get really a washer. So in this scenario, the x is the variable because I will be rotating, I will be splitting this into interval and covering the solid with those washers, one next to each other. If I rotate about the y-axis, so this is the same region, perpendicular, these are my slices. And when I rotate this, I'm getting definitely this washer. And here, y is the variable. Okay. In the shell method, the same, but the slices are parallel. So if I take the same region, and let us say I'm rotating about the y-axis, these are my slices parallel to the axis of rotation, and as you can see, they generate a shell. Y is the variable. Right here, rotate about the x-axis. These are my slices. Rotate them in your head. Definitely they are generating here. I wrote something which is nonsensical. You guys correct me. So this is x is the variable. Right here, that's the interval. Y is the variable. So let me make sure x is the variable. So now I'm going to give you a graph, a picture, easy one. And you tell me immediately which way is easier to do it, shell or washer, and what's the difficulty with the other approach. So what's the easier and what's the difficulty with the other approach? Are you with me? So I'm going to do basically simple. So I'm going to give you the following region. So which is easier? And what's the problem with the other approach? Okay. So I want two answers. So this is my graph. So example number 1. This is the graph. Very simple graph. Okay. Y equal 1 over x. So that's the region. And this is 0. This is 1. And let us say this is 4. Oh, sure. Uh, Sorry, one of your classmates want this one. All right, I'll give you a second to finalize this. When you're done, let me know. Done? Thank you. All right, so this is really my graph, very simple graph. So that's the region. And I'm going to rotate about the y-axis. So question to you, which approach is easier, shell or washer? And second, what's the issue with the other one? So what's the easier? Washer. Why washer is easier? If you do the washer, that's the axis of rotation. So my question, which is easier, shell, let me rephrase my question, shell or washer? That's my question. All right. So if I do the washer, you guys don't write, just listen. How the slices are. The slices are perpendicular to the axis of rotation, correct? All right, what is the issue? What is the problem with this? Okay, I want you guys to comment. Okay, do you guys agree with your classmate the washer is easier? Exactly. If you do the washer, you have difficulties. And let me tell you what the difficulties is. If you take this piece and you rotate it, the inner radius is 1. The outer radius goes from the axis of rotation to the curve 1 over x. If you take a slice right here. If you take a slice down here, the inner is 1. The outer follow a totally different formula. So as your classmate said, we have 2 different bounds. So if you want to take the washer, which is I'm going to do just to fully explain it, you have 2 bounds. You have 1, the outer in this region is going to be this curve. The outer here is going to be this line. So washer will require 2 different bounds. What about the shell method? Is it easy in this case or hard? What do you think about the shell method? Easier. The shell is much easier. Okay, because if I take a slice here, any slice, this is my xi, and I rotated the radius xi, there is no question with it. The height is the 1 over xi. There is no problem with the height. That's the height. And this is my radius, and this is my thickness. So if I rotate this piece, is definitely much easier. Okay, so definitely the shell is much, much, much easier in this scenario. No comparison. And if you use the shell, the volume would be integral from 1 to 4 of, integral from 1 to 4 of 2 pi times the radius, which is x, times the height, 1 over x dx. So basically, it will be 2 pi integral from 1 over 4 of dx. It means it's going to be 2 pi x times 3, which is the 6 pi. So the shell is absolutely way easier in this scenario. Now, to push you a little bit, I don't have to, but let me push you. Let us say, and I hope none of you will do it that way now. Let us say we use the washer method. Let us say we use it. Let us say we do that. So what is going to be the situation? What's going to be the situation? This is my graph. This is my 4 in here. And this is my 1. So we have to be very critical of what we do. If I use the washer's method, as I mentioned a minute ago, when you're going to take your slices, the outer radius between a piece here and a piece here is going to be very different. So the only way you can do it is you have basically to cut at this stage right here. Right there, you have to cut. And you're going to call this D1, and you're going to call this D2. So the volume is going to be volume obtained, total volume, by rotating D1 plus volume obtained by rotating D2. So you have to split into two different regions. You have no way out. And let's do each one of them separately. The volume obtained by rotating D1 is equal to, all right, if I'm going to use the washer, it means my variable is Y here, because I'm covering it with those slices. My variable is Y. Okay. So in this case, for D1, I'm going to take, this will be the interval I'm going to be interested in. So for now, in your head, you have to totally hide this piece, totally hide it, and focus on that one. So my limit are going to be, this is y equal 1 over x. So this point here is 1, 1. And this point here is 4, 1 over 4. It means this is going to be equal to the integral from 1 over 4 to 1 of pi times the outer radius square minus the inner radius square. The outer radius is going to be from here all the way to here. Means the horizontal distance from the axis of rotation to the outer curve. To be able to do that, I need to solve for x in terms of y. But if you do it because of the nature of the function, x here is 1 over yi. So this would be 1 over yi square, 1 over y square minus the inner one, which is 1 square dy. Okay, and then I will have to do that. So that's for D1. Now the volume for D2. So as you can see, it's way, way, way more complicated. It's going to be the integral. For D2, I have to subdivide this integral. So it's going to be integral from 0 to 1 over 4 of pi times. What's going to be the outer radius square? And what's going to be the inner radius square? Quickly, so we can quit. So if I am in D2, right here, it means this is my piece. What's going to be the outer? Exactly. The outer is going to be 4 square. The inner is going to be 1 square. And then you fix every one of them. Okay, so that's to give you an idea. We will never do it this way. That's my point. But just give you an idea that you have to be very careful when you are working with those functions. All right, so that's it for today. As usual, tomorrow you guys will have a quiz, and I think you know what your quiz is about. Everything, this washer shell, and different type of axes. Y-axis, lines parallel to the y-axis, and line parallel to the x-axis, and so on and so forth. Okay, please make sure you do the homework for tomorrow. Any questions? Okay, I have, if you guys here, I have a question for you. One of your classmates told me yesterday that she has a lab at 12 o'clock. Does any one of you has a lab at 12 o'clock and you're having difficulty handing the quiz on time? Okay, nobody? All right, so see you tomorrow then. If you guys have no more questions, see you tomorrow. Bye, guys. Arthur, meet me, Arthur, in my office hours. Arthur, do you hear me? Arthur, meet me in my office hours right now. Okay, bye, guys.